condense a lot. And please keep asking questions. So I want to start importing Tannakian ideas into representing categories of one-dimensional topological things in QFT. Again, I think I mentioned many of these ideas go back a long time. Certainly in math, they go back to the late 30s. But also in physics, sort of implicitly they're around in like representing lines and Chern-Simons as VOA modules, and they touched on Lustig correspondences, and in Dan Fried's work on digraph-Witten theory, they keep resurfacing over the years. Kevin Costello and collaborators has a lot of work on Koszul duality in studying lines and defects in higher dimensional theories, and work on like Yangians coming out of 4D Chern-Simons. That is all underpinned by Tannakian principles. If you look at Kapust and Witten and their description of geometric Langlands and how it's related to 4D Yang-Mills, they describe the geometric Satake correspondence in the Satake category and its relation to rep G by importing Tannakian ideas into 4D Yang-Mills. I guess what I want to say sort of assembles these ideas together with some recent work that I did with Wenjun Liu and related to things that Theo Johnson-Fried and David Reuter have been working on. But I'm going to be super basic, I think, here, and I'll probably still only get through about half the things that I want to say. Let me do a quick review. I think for this audience, it's probably not necessary, and this is going to be too simple anyway. So what do I mean by Tannakian ideas or reconstruction in highly oversimplified manner? So given a category C, if we want to represent it, let's produce a functor. That's nice. And what does nice mean? If you're in an abelian world, to be exact, if you're in a DG or a infinity world, and I'm no longer distinguishing between those two, exactness is automatic. But the thing you need to ensure is that it's continuous. Which means it commutes with limits and co-limits of objects. DG categories include complexes of objects which can be very big. And the typical way to describe a DG category is by taking some small set of objects and then building limits out of them. And the way you get any sort of control is by just working with the set of kind of small objects. And then you need this to be with limits. And by vect, I mean whatever is appropriate for the setting you're working in. Either ordinary vect or DG vect. And in the sort of BV physics setting I care about, there are two different gradings around, and I want vect to have all the gradings. So it's going to be super vector spaces with an additional cohomological grading. So given such a functor, then you do a thing that's actually can be quite hard in practice. Look at natural transformations from F to itself. And realize that by definition of what a natural transformation is, you get an action of A on all of the vector spaces in the image of the functor. So all the things on the right-hand side get an A action, and you get your representation of the category. In fact, even if you don't know what all the natural transformations are, take some subalgebra of them, and you'll get a representation. Great. If, as a remark, it's not hard to find functors from a category to vect. Take any object. In C, and hom out of it. Then if B is nice enough, then A is the endomorphism algebra of B, and you end up reproducing the Yoneda lemma. This thing. Well, this is the Yoneda embedding. So not fancy stuff. One thing you might want to worry about is when this representation is actually an equivalence. And The typical math answers to that, which those of you who actually work with this know better than me, is that F has to be faithful in a sufficient sense, depending on what setting you're working in. If you are humming out of an object, that object needs to be a generator of your category. And if you want the functor to be continuous, the object needs to be compact, stuff. And the other question is, if the category has additional structure, say tensor products, braiding, etc., how can one reconstruct that structure in the algebra A? And that's really where Tannakian ideas start coming in, rather than just saying I'm just doing your Nada embeddings. And the answer to the second question really depends on how F plays, preserves or not, the tensor product, braiding, etc.
So, I mean, does this say more than just the Uneta embeddings monoidal?
It may or may not be, depending. Yeah. I mean, typically, if you're just humming out of an object, it is not.
If it's an algebra object, it is.
Right. So if it's an algebra object, you can make it so, but then it's still. I think it might at best be lax monoidal.
Yeah, right.
And then so like the best possible situation, which is what I want to get to, I hoped at the end of today, but it might not happen, is that if you have a monoidal category, you can turn A into a Hopf algebra. But that's really asking a lot. And typically that's actually asking way too much. But I will discuss what you need, and I'll discuss in QFT terms what you need to turn A into a Hopf algebra. Okay, so let me forget about monoidal structures for now and just draw some pictures of Fs. I don't know whether I should call them fiber functors or not if I'm not considering monoidal structure. I'll use the word anyway. Though some people would consider like a fiber functor a thing that is not just monoidal but has some very strong other properties. This sort of setup appears in two-dimensional topological field theory, and that's sort of the most fundamental place it appears, and any other setting can be reduced to a two-dimensional TQFT. So Fs come from 2D TQFT or reductions. There too. Where C is a category of boundary conditions. Now, in two-dimensional QFT, if I don't immediately assume that the theory is oriented, there are categories of boundary conditions associated to every single angle that might be a little bit different and have isomorphisms between them. A priori, there is a different C left and C right of left and right boundaries, and some isomorphism of swinging around by 180 degrees that relates objects in C left to C right, and you can swing back around, but the total 360-degree isomorphism may not be the identity, and that's a thing called a Serre functor in the category. I'm just writing these as different things for now. And the question I want to ask is how to represent C right. And I'll do that by choosing any boundary in C left, and I'll call it B left, and I'll define F from C right to vect to be, so it sends any right boundary. Yeah, sorry, I didn't want to make this big because it's a thing I'm fixing. It sends any right boundary to the space of states on the strip between the right boundary that can fluctuate and the left boundary that's fixed. And in TQFT terms, that's a TQFT functor applied to an interval between B left and B right. And I can also think of that, there's this state operator correspondence around. So if this is actually a data construction, if I flip B left around to the right side and put everything on a half space with the dual of B left and B right, then states on the strip are the same as local operators between B left and B right, and so this is actually home in the right category. Between B left dual and B right. Okay. And then with that, I sort of want to change the points. So that's my functor, and it's endomorphism algebra. What is it? I really should have drawn this picture much bigger. Let me draw it bigger here. So the fiber functor takes any right boundary condition So the space of states between my favorite left boundary and the right boundary. That's the sandwich. And end of that functor is things that local operators. So I should maybe explain why this is. So it's local operators on the left boundary. But let me say that better. So these are natural transformations from the functor to itself. At the bottom of this strip, I've got the functor. Applied to something. And I'm sort of, that can be anything, and I'm not allowed to touch what that anything is. There might even be morphisms between different things over here. This fluctuates. I've got the functor on the bottom, and I've got the functor on the top. A natural transformation of that functor is any operator that sits in this region. It's got to have finite extent and time because it goes from FB left to FB left. And it can't touch the right boundary because that's where things fluctuate, and that's what I'm applying it to. And I'm left with some big half-disk region where I can modify. But the theory is topological, and any big half-disk region like that shrinks to a local operator attached to my favorite B left, which is why, in physics terms, the endomorphism algebra of this thing is just the algebra of local operators sitting on B left. So this is, call it A left. It's just n in the left category of B left. And then you can go on and describe it in several different ways. So I could mess with the state operator correspondence again and say, if I've got a local operator there on B left, that's the same as a vector space. The space of these things is the same as the state space on a strip between B left and B left dual. There are lots of games one can play. Possibly I'm playing too many and confusing you all, but that's actually the same as the fiber functor applied to be left dual. Okay, great. So that's roughly how functors like this show up in 2D QFT. You just evaluate sandwiches. And then you start to ask the more interesting questions of when do you get an equivalence? And can you do anything more? So, sorry, did that make sense? Too boring or way too confusing? Okay. So one is F left and equivalence. I think I want to relax that a bit and just say when is it faithful.
That equivalence you write down here, you mean something like this?
Yeah, I totally do. Yeah, so like here.
Yeah, the right side is, maybe you can write it as this. And you open it.
Yeah, that's exactly what I have in mind. So I'm opening and closing and. Yep. Okay. So you can answer this question in a math way, and just say, well, roughly this is humming out of an object. So you expect that B left dual should generate C right, or C left. Generate C left. Fine. But I sort of want a more concrete thing that I find easier to check in practice in a physics setup that will end up implying that B is a generator. So more concretely, we'll ask that this favorite left boundary condition of mine is complete. And I mean the following by that. This means that there exists a big B right such that the pair there's B left, there's B right. The pair of back-to-back big B boundaries deforms to the identity interface. So really, it's not just the existence of B right, but it's B right and a deformation. And where does that deformation live? It lives in the algebra of operators on the two boundaries. And the whole reason I went through a whole ordeal with deformations is so that I wouldn't need to explain now what it means to deform. If you're in some finite semi-simple context, then probably what you want to think about by deforming is the finite deformation satisfying a projection equation. And if you're in a DG context, you find a more Cartan element and deform differentials to do this. And then there are exercises that somehow whose answers are really important in getting your head around things, but probably not important for the rest of these lectures. Completeness implies lots of things. So completeness implies that both BR and BL are generators. Specifically, let me just take one of them. Any object in the right boundary category can be written is equivalent to taking my big BR, tensoring it with a vector space, and deforming. By a suitable Moore-Cartan element or projection. So they're not only generators, but they're generators in a very strong, precise sense. I sort of want to draw the picture for that. So why does the completeness condition? And I'm calling it completeness because this is like the categorical analog of complete bases of states in quantum mechanics. These are the things you insert to glue together Hilbert spaces. And just at one category level up. So where does this vector space come from? So suppose that I've got a right boundary. How do I find that vector space? I think I want more space. Suppose that I've got this right boundary. How do I find the vector space? I sandwich it with the left. With the left element of the complete pair. Then what's the Moore-Cartan element? Well, to take this vector space and reproduce the original boundary condition, I consider the BL-B right sandwich and my vector space, the BL-B sandwich, that's V, and deform with my special Moore-Cartan element. And I can view this in two different ways. I know that if I sort of think of both of the sandwiches as having thickness and deform first, that is equivalent to, sorry, I don't actually want to keep that open, apologies. So half space attached to V and deform. If I deform first, then I end up with a half space with the original B boundary. Because the deformation just cancels out the B right BL pair. On the other hand, what is this? It's B right tensored with a vector space. And mu B is just the image of the canonical thing. acting in endomorphisms of, write it the other way, acting in A right times endomorphisms of VB. And it obviously acts in endomorphisms of VB because it's like acting on this side. Okay. That's the construction that sort of underlies everything, and that's what you can. You not only use this to show that both sides are generators, but it makes the representation theory extremely explicit. It not only tells you how your lifted functor goes to modules, but it tells you what that module is. It's this space that's reconstructing your object. Sorry, questions, thoughts?
This is somehow a re-expression of the coordinator lemma, right?
Yeah, I think so. Yeah, totally. I think all of my talks are re-expressions in pictures of basically one of them. Thank you. The other thing I should say is that if you actually want to make this rigorous, you need to be careful about orders of limits, and that's where you actually need your functors to be continuous and commute with orders of limits, because there's some order of limit in squeezing and deforming that happens here. Okay. The other thing I want to say is that there's another nice condition you can impose on your boundaries, which is transversality. So we'll say that a pair B left, B right is transverse if the state space on a strip is isomorphic to C. Is trivial. And there's more sitting behind this isomorphism. I mean it at the correct categorical level, which in this case means that there's right. There's some little interface between them that actually manifests that isomorphism and can be inverted. It's the other way. Transversality is incredibly nice when it exists because it lets you, yeah, well, it leads you to Koszul duality.
Sorry, Tudor?
Yeah.
Would a similar cartoon be the same for complete, where you have B left and B right joining with the dot? I could do it in the other direction and have the identity on top. Is it the correct count?
At least in the finite case, yes, you can deform in a half space. I'm actually not positive about the answer in general. And you don't need it you don't need it for these statements. And in higher dimensions, the answer is no. And like it's not actually possible. You don't need it, and it's not possible. In examples, to find a completeness condition that strong, that actually gives you an isomorphism. If you're gauging, there may be some anomaly to gauging in a half space. In 2, there certainly is in higher dimensions. In 2D, you're like literally just inserting projectors, and it should probably be fine. So the answer to your question in a discrete case in 2 dimensions is yes, but I would be wary in general. Great. So yeah. So actually transversality is a thing that in higher dimensions is going to lead you, as I'll try to explain next time, to the structure of actual Hopf algebras and really nice co-products on the nose. In 2D, it leads to what's known as Koszul duality. Let me just say what that is, and then give a bunch of examples of this entire setup. If you can find transverse and complete boundaries, and be right, then you end up with a bunch of really nice statements. The space of states on a strip between BL and B right is isomorphic to C, but it has an action of both algebras, A left and A right, and they're guaranteed to be mutual commutants of each other. So AL is end of the trivial module in AR mod, and A right is end of the trivial module in A left mod. And the two categories are equivalent up to maybe some up. So C left is a right mod, and C right is a left mod, But there's an isomorphism between these, rotation by 180 degrees. Which is an isomorphism that swaps orders of Homs. Moreover, the fact that the strip state space is trivial means that the tensor product of the two algebras can be deformed to the identity. So if you squeeze the strip together, you'd better get something trivial, even though like the right-hand side is non-trivial and the left-hand side is non-trivial. Whatever is happening in the bulk here makes the left and right interact in such a way that you just get something there. Which means there's a more Cartan element that deforms these things. To trivial, which here this is endomorphisms. Endomorphisms over C. This entire package is what one means by a left and a right being Koszul dual algebras. And one typically doesn't start with the entire package. You say start with one of the algebras, say a right. Its Koszul dual is, you start with one of the algebras mathematically and a trivial module. Define the Koszul dual as endomorphisms of the trivial module, and then derive that its module category has to be derived equivalent to modules of the original thing. And that's the actual statement of Koszul duality. And I'm saying this just to point out that it fits inside this entire setting as a special case when the generators you've taken are transverse. Now, that's all well and good, but in 2 dimensions, swap boards. In 2 dimensions, that really special setting typically doesn't exist, unless you're perturbative. And then there are tons of examples. So in 2D, transverse and complete boundaries typically, well, they require a DG setting. I'll say that. Let me just give you some examples of the entire setup before I stop. So let's take 2D finite group gauge theory. This is probably a setup you're all familiar with from in particular Konstantin's work with Dan and Greg Moore. So we be simple about it and set the 2 cocycle to be 0. And I want to represent a category of boundary conditions. I know that in gauge theory, there's always one distinguished boundary condition called Dirichlet. And because gauge symmetry is broken on it, it's got a global symmetry. There are local operators corresponding to elements of the group. So end of D is the group algebra. So I get a representation of the category here to P. Awesome. And then you can ask, is that representation faithful? And then the whole completeness analysis I find useful in working through this mentally is D complete. It is. If I stack D back to back with itself up to some orientation reversal, I can gauge a diagonal symmetry. I can throw in a more Cartan element. That's a sum over group elements of G acting on the left and G acting on the right that ties together these global symmetry transformations with some factor that makes it a projection. I'm sorry, I said more Cartan. Here I just mean the finite projection. It satisfies the finite version of the equation. U squared equals mu. And that's, you can think through that and realize that that's equivalent to the identity interface, so certainly D is complete, and then you can work through the rest of the analysis. So indeed, boundary conditions here are rep G, and a nicer way to say what they are is that they're a Neumann boundary decorated with Wilson lines. Those are the actual representations that we get. Great. So there certainly are complete boundaries here. There are not transverse and complete. So N and D are transverse. Neumann and Dirichlet are transverse. The N sandwich is trivial. Why? Because Neumann is the trivial representation. That's one way to say it. Or here you've gauged, here you've fixed the gauge symmetry, and there are no degrees of freedom left. But Neumann is not a generator. It's not complete. And I think that's a special feature of two dimensions. In higher dimensions, Neumann does generate. And it has to do with the fact that Wilson lines are the same dimension as boundary conditions in 2D. I think I'll say more about that later. But N does not generate. This is a weird two-dimensional feature. I want to give you one more example. I'll do it here. Let me do perturbative gauge theory. So the algebraic gauge theory. In BD. The bulk fields are a multiform including the connection. And now we're in 2 dimensions, so there's a 2-form descendant. And dual thing. So this is topological gauge theory. In 2 dimensions is BF theory. The action is BDA plus some interaction term. And let me just say what the answer is, because I'm running out of time, and you guys need a break before the next talk. So the upshot is that this has transverse and complete boundary conditions. D and N is Dirichlet, and its endomorphism algebra is infinitesimal gauge transformations, which produce the enveloping algebra of the group. And it's kind of pretty to see where they come from in terms of Feynman diagrams and A-infinity structures, but that's not happening in the next 10 seconds. Similarly, N is Neumann, and there's a pretty Feynman diagram way of explaining why its endomorphism algebra is no longer trivial. Whereas here, for a Neumann boundary condition in finite gauge theory, part of the way to see that N can't possibly generate is that its endomorphism algebra is trivial. There are no local operators on Neumann, but now there are. And that's Chevalier-Eilenberg for G. In other words, it's the ghost complex. It's generated by the ghosts with the Chevalier-Eilenberg differential. And the upshot is that the category of boundary conditions can be represented either way. So C is either enveloping algebra modules or Chevalier-Eilenberg modules. They are derived equivalent. And they're both representations of the enveloping algebra. Rep P is Schumann is Chevalier-Eilenberg mod. Let's see, one last sentence. If you make this non-perturbative, you get something very similar to the finite group case. So I very specifically use Lie algebras. If you use a Lie group, then nasty things happen, sort of. On Dirichlet, you get finite gauge transformations, and this becomes distributions on the finite complexified Lie group. And Neumann becomes derived invariance of the trivial module for a global Lie group, which is trivial. And Dirichlet generates, and you get the right thing, which is G, rep G, modules for distributions. Rep Neumann is certainly not correct, and it's not correct the same way that it wasn't in the finite case. Cool, thanks.